Scientific approach to knowledge. The scientific approach to knowledge is different than a philosophical, it's a long word, philosophical approach to knowledge. We don't just sit around and think about things. We actually do something. It's empirical, meaning it's based on observation and experiment. So the scientific method is the process by which scientists seek to understand nature. We make observations, we conduct experiments, and so the key characteristics here are observations of what happens, formulation of hypotheses, our best guesses as to why that's happening, experimentation to test that, and then formulations of laws and theories. And we'll talk about each of those individually. Observations are also known as data. This might be the mass of an object, the temperature, the speed at which something is moving. There's lots of different kinds of data. Observations are descriptions of the characteristics of matter or its behavior. So we'll use an example that your textbook goes over. Antoine Lavoisier was a French scientist. He lived in the 1700s. I'll be mentioning scientists' names and the dates that they lived throughout the semester, but I'm not going to test you on them. So you don't need to remember what the dates were that Lavoisier lived. But he was a very famous and influential scientist. He did some experiments involving combustion. So let's think about, we probably all have at least once sat in front of a fireplace, right? It's becoming less common because they put all these restrictions on us about burning wood. But you light the log on fire and it burns and it's pretty and warm and everything. And then what do you have left afterwards? Charcoal or ashes, right? Do the ashes weigh more, less, or the same than the log you started with? They weigh less, right? A lot less. That log, you might have had to put it in there yourself. It was heavy. You scoop those ashes out, and they're very light and fluffy, and you little breeze, and they blow all over the house, right? Make a mess. Lavoisier was interested in what's going on with that. And so he did experiments, and he made observations. So he burned things in closed containers. And what he observed is that there was no change in the total mass of material inside that closed container when something burned. When you burn a log in the fireplace, it's not a closed system. Things can go up the chimney, things can come out into the room. So he did these experiments in a closed container. He observed there was no change in mass. So observations like that lead scientists to a hypothesis. A hypothesis is a tentative interpretation or explanation. Why do you think this is happening? That's the question you're answering when you make a hypothesis. So Lavoisier explained his observations by hypothesizing that when a substance burns, it's combining with something that's in the air. The mass of the substance that burned by itself is less afterwards. But the total mass of the system was the same. So he's saying, well, there's just some rearrangement going on here, and it must be combining with something in the air. That was his hypothesis. Now, you can have lots of crazy hypotheses as well. You could hypothesize that there are little invisible elves that come in and do something magical inside that closed container. Is that a hypothesis? Sure. Can you test that? How do you detect invisible elves? I don't know. I keep waiting for the cleaning elves to come to my house and do the dishes. It's not working out so well. In order to have a good hypothesis, it needs to be falsifiable, meaning you could test it and possibly prove it to be wrong. We test these hypotheses by experiments. An experiment is a highly controlled procedure designed to generate more observations. So how might you test the hypothesis that the object burning combines with air? Well, You could try burning the object in a container that had no air and see what happens. If it combines with something in the air when it burns, and you burn it with no air, what should happen? It won't burn. If it has to combine with something in the air, then it won't burn. So that's a testable hypothesis and an experiment where you could test that. So you do the experiments, and sometimes they support your hypothesis. Things go as you thought they would, and you're like, yes, I'm right. And sometimes it just doesn't work out at all, and you're like, oh, well, my idea was crazy. Sometimes you just have to throw the hypothesis out. Sometimes you can just tweak it and revise it and go on. But then that new hypothesis needs to be tested again. Scientific laws are a little bit different. These are brief statements that summarize past observations and predict future ones. These are not a hypothesis. This is really more of a established observation. You're familiar with the law of gravity? That's a physical law. So here's a Sharpie marker, and I'm holding it out. If I let go of this Sharpie marker, what does the law of gravity predict will happen? It'll fall, and it does. Every semester it does that. It did that yesterday in my class too. Law of gravity. It allows us to predict what's going to happen in the future. Laws are very useful. A law that came out of Lavoisier's experiments was the law of conservation of mass. That states that in a chemical reaction, matter is neither created nor destroyed. And here the Lego analogy is useful. Let's say you built a rocket ship out of Legos. So you have this substance, this rocket ship, and then you take it apart and you make it into a giraffe. Is the mass of the Lego pieces the same? Did you lose or gain any Lego pieces? No, all the Lego pieces are there. Maybe you chose not to use all of them in your giraffe, but they're still there on the table or on the floor. Lego pieces do not appear and disappear. Sometimes we think they did. There's that special piece you need, and it's just gone. You can't find it anywhere. It's actually there somewhere. And that's how matter is. It's a rearrangement. There's no creation or destruction of the matter. We're also familiar with state laws. State laws, federal laws. There's a speed limit. That's a law. You're not supposed to go above the speed limit. And if you do, something bad, could happen to you. You can choose to disobey laws made by the government. You cannot choose to disobey scientific laws. You can't say, well, I am not going to obey the law of gravity today. And I don't want to take the stairs. I'm just going to jump off the balcony and just float down gently because that's what I want to do. You can't do that. The law of gravity is always in effect. A theory is a well-established hypothesis, basically. So scientists make observations, they develop hypotheses, they test them. Once that hypothesis has been tested repeatedly, that may give rise to a scientific theory. So after Lavoisier's time, but based on his work, John Dalton came up with atomic theory to explain the law of conservation of mass. The law says what happens. The theory explains why. He proposed that matter is composed of small, indestructible particles called atoms. So he says, well, the reason the mass doesn't change is because it's composed of these little atoms, like the Lego blocks, and when you have a chemical reaction, all that's happening is you're rearranging the atoms. You're not creating them or destroying them. You're just taking the Lego blocks and putting them together in different ways. So the scientific theory is a model for how nature is. It tries to explain not only what it does, but why. And scientific theories are very useful for predicting what's going to happen in the future, when you try to do stuff with matter. Theories also need to be validated by experiments. You cannot conclusively prove a theory to be correct. And that's disturbing to some people. What do you mean you can't prove something to be true? Well, we can't. We could sit around later and discuss things like, prove to me that you exist. Have you ever done that in class? It gets really hard. Start to think about that and make your brain hurt. You can't prove that something's true. So when we have a theory that we accept as correct, all that means is no one has come up with a situation where it doesn't work. And as we'll see, theories get revised as science and technology advances and we learn more about nature. We realize, oh wait, that theory worked for this set of circumstances, but now that we know about this other stuff, we need to revise the theory. But until that happens, the theory is accepted as true. I kind of already said some of that. A well-established theory is as close to truth as we get in science. Sometimes in everyday life, you'll hear somebody say, oh, that's just a theory. Well, if you have a theory about why your kid's wetting the bed, it's just your guess, what you think. In science, a theory is very serious. It is something that's been tested by lots of people, and it's as close to truth as we can get. So we never say, well, that's just a theory. Scientific theories are very serious. So this whole idea of the scientific method, some people think that science is very tidy and that you do this and you do this, you follow these rules and you get this predictable outcome and everything's all nice and you tie it up with a red ribbon and you're done. Science is actually very messy. But that also makes it very interesting because you make an observation and you get a hypothesis and you test it, and in the process of doing that, you make other observations, and it's like a tree branching out, and you're an ant crawling up the tree, and you're like, oh, I could go down that branch, I could go down this branch, I could go over here, and the possibilities are almost endless. But there's not a rigid set of things that we do. This is a flow chart of the scientific method. Observations lead to hypothesis. You have to test the hypothesis by experiment, and the experiment can either confirm or cause you to revise your hypothesis. And sometimes you'll go around in this little loop many, many times before you find a hypothesis that the experiments support. Observations can lead to laws. Laws are going to also be tested by experiment and confirmed or revised. A good hypothesis can lead to a theory, but the theory also undergoes constant testing to be confirmed or revised. Scientists are curious and they're also very skeptical. And so somebody will publish something in a scientific journal and say, if A plus B gives you C, and the scientist says, I'm not sure I believe that. I want to see if I can do that myself. And so they'll set up the same experiment in their lab and try to reproduce what the other person did. And so there's all this testing that goes on, and one of the fun things to do is to prove somebody else wrong, right? And so there's a lot of that goes on in science. So what do you need to know about all this? Well, one of the things you need to do is be able to distinguish between a law and a theory. So which of these statements best explains the difference? Let's look at them one at a time. A law is truth, whereas a theory is a mere speculation. Does that sound good? No. A good theory is as close to truth as we can get. It's not just mere speculation. So that one's not right. I'll cross that one off. A law summarizes a series of related observations, while a theory gives the underlying reasons for them. That sounds pretty good. Let's not decide until we read all the options. A theory describes what nature does, a law describes why nature does it. That one's exactly backwards. So that one's not right either, so this is our correct choice. Any questions?